The second and final type of nuclear reaction we're going to study is something called nuclear fusion. And basically, fusion gets its name for when two or more atomic nuclei fuse or join together to form a single nucleus of just a slightly smaller mass than you might expect. The most important one of these, of course, in our everyday life is the sun. So basically, when you look up at the stars at night, every single one of those stars is a sun in its own solar system. And all of those are big balls of gases undergoing intense fusion reactions, making an incredible amount of heat, an incredible amount of light, and of course, incredible amount of energy. An example, as you guys can see right here at the center of your screen, at the first level, we're going to take two hydrogens together and collide them to make a larger nucleus. We're going to add another hydrogen to make it a larger nucleus, and so on. And again, in the process, we do create some other smaller subatomic particles, but eventually, again, we're making bigger nuclei as we go along. Now, like it says at the bottom of the screen, this produces a very, very high amount of energy, which is, again, why we are trying to build a fusion reactor in order to harness that for civilian electricity production purposes, which we'll talk about here in just a moment. But on the flip side of that, because it releases such an insane amount of energy, we have also, gone the other direction and built what we call hydrogen bombs, which are way more powerful than the traditional atomic bombs. And again, we'll get to that in just a moment as well. Now, fusion reactors and the potential for production of power, like it says here. So fusion produces no waste, literally zero waste. So if you remember, fission does produce nuclear waste, and nuclear waste is going to be nuclear and radioactive for a very long amount of time. As long as we can contain it and put it somewhere safe where it won't be disturbed, then it's okay, right? We could kind of just let it decay over time, but we can't speed up that process. We just have to store it somewhere. Fusion, on the other hand, excuse me, on the other hand, produces no waste at all. There's also plenty of fuel available. Basically, we need hydrogens, and hydrogens, we can get 2 of them for every single water molecule. So the fact that 70% of the planet is surrounded by oceans, literally we have more fuel than we could possibly even imagine. So again, if we could produce a fusion reactor, it would produce no waste, an incredible amount of energy, and we would have an abundant fuel source that's basically almost, for all intents and purposes, limitless. That is very exciting, very exciting. Now, the major problems with fusion reactors, again, that we are trying to develop, is the extreme amount of energy that is required in order to even get it to start. Very, very difficult to even get the fusion reaction to begin. The extreme cost to produce the required energy to initiate. So again, if we're trying to do the top one, the amount of money it would cost to make that energy is at the moment not necessarily prohibitive, but to do it on a large scale, it absolutely is. To do it in a very small scale, say, and testing, that's something we can do, but to do it, across the planet in all the different countries, no, we just can't do that yet, okay? We still need to develop a workable fusion reactor and then scale it up to something that we could actually use to power cities, right? But we're not quite there yet. So the way this basically works, or at least in theory, and again, like I said, people are working on it as we speak, is we have, basically it's gonna look something kind of like this. This is just a schematic. So what you have here is a whole bunch of magnets. All those copper looking things are magnets. We have one in the center, which is kind of a coil. And then we have some all around the outside in different directions. So what this would work, or how this would work, is we would superheat the gases into the state of not a gas, but into a plasma. So you guys will notice right here, it says the plasma current. So it would be going around like this, around and round, around and around, and the magnets would hold it in that circular pattern. So as it travels around, being confined by the magnets, it would heat up and heat up and heat up and heat up, eventually to the point where we could actually start to fuse nuclei together. And the fact that the magnets, again, are orientated in such an interesting way, the plasma, as you can see by the yellow and the green, would actually be spinning as it goes around. So spinning as it goes around inside the reactor. And that's how we hope for it to work. Now, if you remember back for a fusion reactor, there's not a lot of movement. We have the fuel rods, they just sit there inside the reactor. We have the control rods, which we lower and raise into it in order to speed up or lower the reaction. Here we have the plasma, which is super heated. And again, it's whizzing around inside this interesting little donut shaped reactor, and it's getting hot as it moves around. And hopefully, again, the nuclei will collide and actually begin to fuse. And as they do that, they will create a lot of energy. Now, again, so this is more of a realistic one of what we're actually trying to build. Notice the magnets are all in really weird angles. Again, shown here kind of as an orange color and the red color. And again, that's the kind of the interior view at the very bottom. At the top would be the exterior view, a little bit more, again, more accurately represented. What we have right here, again, is a small mock-up of one. You can see the gentleman on the right inside of it. Obviously, it's not working right now. But again, we're trying to get to the point where we could actually get this reactor not only to power up, but actually to start spinning the plasma, which we could do, but to get it hot enough to actually start to begin fusion reactors. Again, that's not very easy. So now that we have these, we're actually starting to scale it up to be quite larger. And if you guys will notice over here on the right side, again, there's a person right there. And so you can see that this one is a far larger reactor from the interior view, when you could easily walk around. And again, eventually we'll get hot plasmas whirling around this at high speeds and extreme temperatures. So that's what a fusion reactor will hopefully soon look like. Again, we're getting very close to this. And again, this could revolutionize humanity probably like nothing else before, in that we could have limitless energy. Now think about all the benefits of having limitless energy. Literally, we could do the cost of electricity or the cost of power would no longer be an issue for anything. We would have limitless power. That again is pretty exciting, in that one of those things that hold us back from advancing our society and new inventions and new creations is often the cost and the power associated with that. Well, that would be wiped off the table. That is conceivably where this could lead. So it's a very, very exciting. Again, nuclear fission reactors are very clean. They operate every single day, and every country, almost every country, has many dozens of them. And again, we never hear about them. So nuclear fission is quite safe. Again, it's kind of like, I was talking to another teacher about this. It's kind of like airplanes. You know, airplanes, they fly thousands, tens of thousands of flights a day, you know, without any issues. The only time you ever hear about airplanes is when they crash. It's kind of the same thing with fission reactors, which we talked about in the previous video. They operate safely every single day. We only hear about them when something goes wrong. Again, fusion reactors, which we're talking about right here, again, are a big step forward. No nuclear waste at all, and no waste, period. So like I said, if we could do this, limitless energy and no drawbacks, except for, I suppose, if we had some sort of issue happen to the reactor itself. But again, this is a very exciting place that we're trying to go towards. And again, hopefully we'll be able to get this soon, but we are definitely working at it as fast as we can at the moment. So like I said, very exciting.